In this video, we're going to learn how to graph functions. Each time we graph, we start by identifying the parent function that our actual function is derived from. Parent functions, or basic function categories, give rise to all other functions whose graphs have the same shape. They represent the most basic cases that would give graphs that have a specific, unique shape. To determine which parent function our function comes from, we take our actual function and strip off any added, subtracted, or multiplied numbers, and what we're left with is the parent function, which usually represents some special operation being applied to the function input. The graph of the parent function is the starting point for the graph of the actual function we're given. We're going to look at 7 parent functions in detail: the identity function, the quadratic function, the cube function, the square root function, the cube root function, the absolute value function, and the reciprocal function. Keep in mind that these aren't the only parent functions that exist, but they're the only ones we're going to see. We'll graph them by generating a table of xy values and plotting points. Then we'll talk about the domain and range of each of them. The first parent function we're going to look at is the identity function. The rule for the identity function is f of x is equal to x. So in other words, the identity function takes an input and then doesn't change it. The output and the input are exactly the same. So if we use a table of values to plot points, for any value we plug in, we get the exact same value out. This generates a bunch of points that have matching x and y coordinates. So if we graph something that looks like this on a coordinate plane, we end up generating a diagonal line that goes through the origin. Now let's talk about the domain and range of the identity function. So just as a review, remember, if we have a graph and we want to find domain and range, domain is considered the projection of the graph onto the x-axis. So if we were to slide all the points on the graph onto the x-axis, it's all the values on the x-axis that our graph would cover. That gives our domain. Same thing for the range, but then we're projecting onto the y-axis. So all the y values that our graph covers constitute the range of the function. So in this case, our domain is all real numbers. We cover everything from negative infinity on the x-axis to positive infinity on the x-axis. And then our range is also the same, negative infinity to infinity, this case on the y-axis. The identity function is actually the parent function for all functions that generate diagonal lines. So anytime we graph a function and it gives us a diagonal line, the parent function of that particular function is actually the identity function. Now remember, we have specific techniques we can use to graph diagonal lines. So whenever you see a function that's of linear form, make sure you graph it using slope-intercept form, graphing the y-intercept and then using the slope to find another point. The next parent function is the quadratic or the squaring function. The rule for the quadratic parent function is f of x is equal to x squared. So for any input, we square the input. One thing that's special about squaring is regardless of what we input, squaring always results in a positive output. So whether we're squaring a positive or a negative input, our output is always going to be positive. If we graph these points on a coordinate plane, we get a roughly U-shaped graph that we call a parabola. We're actually going to spend a lot of time graphing parabolas in detail in the next chapter. So for this one, the domain is going to be all real numbers. We can plug in any number we want and square it and get a legitimate output. The range, however, is going to be everything from 0 to infinity. So if you look at the graph, notice there aren't any points below the x-axis. All the points on the graph are going to remain above the x-axis. So the smallest y value we can get as an output for this function is going to be 0. Other than that, every single output we get is going to be a positive number. Our next parent function is the cube function. The rule for the cube function is f of x is equal to x cubed. Now cubing is a little bit different from squaring. Whereas with squaring we get positive outputs entirely, with cubing the output depends on the sign of the input. So if we plug in a negative input, we're going to get a negative output. Think of it as multiplying numbers repetitively. If we're multiplying 3 numbers together, if those numbers all happen to be negative, then their product is also going to be negative. So with a cubing function, we can get both negative and positive outputs. So if we were to graph this on the coordinate plane, notice we now have values above and below the x-axis. Our domain for our cubing function is going to be negative infinity to infinity. Again, we can plug in anything we want, cube it, and get a reasonable output. and then our range is also going to be negative infinity to infinity. Because cubing allows us to get both negative and positive outputs, we can get any value we want as part of our range. Our next parent function is the square root function. The rule for the square root function is f of x is equal to the square root of x. So taking a square root is the opposite of squaring. Whereas with squaring, we're multiplying a number by itself to come up with a product. With a square root, we're taking that product and we're decomposing it. So we're saying, based on this particular product, what two numbers did I multiply together in order to get this number? That gives us the result of a square root. So we actually have a different set of inputs to graph this function. Notice all the numbers are positive. If I tried to plug in a negative input to this function, I'm going to get a number that's not defined in the real number system. In other words, if I try to graph it on the coordinate plane, it doesn't exist anywhere on the coordinate plane. So first off, we choose numbers that are greater than or equal to 0. Notice I've also picked some very specific positive numbers. I picked 0, 1, 4, 9, and 16. What all these numbers have in common is that they're all perfect squares. So if I plug them into the square root function, I'm going to get a really nice clean output. That's not to say that if we pick numbers like 2 or 3 or 5 that we can't take the square root of those numbers. However, if we try to take the square root of those numbers, we end up with an irrational number, and we'll just have to approximate it in order to graph. The problem with that is we're going to end up with things that are more difficult to graph, whereas with these particular values, if I plug them into the square root function, I end up with outputs that are really easy to graph as points on the coordinate plane. So if I graph these points on the coordinate plane, I end up with what looks like the parabola turned on its side and cut in half. That's actually exactly what this graph is. It's the square graph, but turned on its side and cut in half. We'll talk more later in the semester about why those two graphs are related in the way they are. The domain of this particular function is 0 to infinity. In other words, we can only plug in non-negative numbers in order to get real outputs that we can graph on the coordinate plane. The range is also 0 to infinity, so whenever we plug in a number to the square root function, we can only get a positive output from it. Our next parent function is the cube root function. The rule for the cube root function is f of x is equal to the cube root of x. So just as a square root is the opposite of a square, the cube root is the opposite of a cube. So when we cube a number, we're taking that number and multiplying it by itself 3 times and coming up with a product. When we're taking a cube root, we're taking that product and decomposing it into the number that we multiplied by itself in order to get that product. So we're saying, what number do we have to multiply by itself 3 times in order to get the number we're taking the cube root of? The cube root is a little different from the square root. With the cube root, we can plug in both positive and negative numbers. That's because when we cube, we can get both positive and negative outputs. So we can take a cube root of any type of number. Notice, however, that I've also picked specific numbers here. So just like with the square root, it's easy to take the square root of perfect squares. With the cube root, it's easier to take the cube root of perfect cubes. So each of these inputs I'm plugging in is something that is easy to take the cube root of. So if we take the cube root of -8, the number we multiply by itself 3 times to get -8 is going to be -2. -2 is the cube root of -8. We get a -2, a -1, and then 0, 1, and 2. Just like with the square root, we could pick other inputs, so we could pick -2 and +2. However, if we try to plug those into the cube root function, we're also going to get an irrational output. So we would have to approximate, and graphing would not be as easy with a point like this. So we pick points like this that are perfect cubes so that they'll be easy to graph on our coordinate plane. When we graph this also looks similar to the cube graph. It looks like the cube graph turned on its side and flipped once. And again, that is for a very specific reason that we'll talk about later in the semester. The domain for the cube root function is all real numbers. I can take the cube root of any negative number, any positive number, anything in between. The range is also all real numbers, so I can cube any number I want and get any number I want, which means that I can plug in both positive and negative numbers, and I can get out both positive and negative numbers. Our next parent function is the absolute value function. The rule for the absolute value function is f of x is equal to the absolute value of x. Remember, we defined absolute value as a number's positive distance from 0 on a number line. So if we were to start at 0 and go to that number on the number line, it's how far we'd have to travel as a positive distance. So we can take the absolute value of any number we want. As long as it's on the number line, it has a defined distance from 0. Note, remember, the practical way of thinking of absolute value is it takes negative numbers and makes them positive, and it leaves positive numbers alone. Well, for our purposes here, it's fine to think of absolute value in that way. So absolute value of -2 is 2, absolute value of -1 is 1, and then so on and so forth, 0, 1, and 2. So we have matching absolute values for both positive and negative numbers. If we graph this function, it actually looks like a V. So it's the identity function, but the left-hand portion of the graph that would be below the x-axis is actually flipped up to the positive side so that all of our y values are positive. So it's closely related to the identity function. The domain for absolute value is all real numbers. We can plug in and take the absolute value of any number we want, and it will be defined. The range is everything from 0 to infinity. In other words, when we take the absolute value, we know we're only going to get positive numbers out. So the range of possible outputs is just the set of positive numbers, everything from 0 to infinity. Our final parent function is called the reciprocal function. The rule for the reciprocal function is f of x is equal to 1 over x. That's just a nice way of saying for whatever input you plug in, you take the reciprocal of it. In other words, you flip it upside down if you were treating it as a fraction. So we have a longer set of inputs because this graph needs a little bit more detail than we've seen before. So for all of our negative inputs, notice that if we take the reciprocal is still going to be negative. It's just going to be the multiplicative inverse, or the flip, you can think of it as the flip, of whatever the number was. Now what happens if we try to plug in 0? 1 over 0 is actually undefined. Division by 0 is not allowed, so we can't actually plug in 0. That's going to correspond to something very specific on the graph that we'll see in a minute. For our positive inputs, again, we just take the reciprocal, flip the number upside down, but in this case, the result is positive. So if we were to graph all of these points on the coordinate plane, we have a very specific, unique looking graph. This graph actually has two pieces to it that are completely separate from one another, and there's a break in the middle of the graph at 0. So one thing that's unique about this graph versus the other parent graphs we've seen is this graph does not have a point at the origin. For all of the other graphs we graphed, they start at the origin and then they continue maybe in both directions or maybe just in one direction. This particular graph is completely open there at the origin. It's not defined when x is 0. So we get infinitely close to 0 on the left side from that branch below the x-axis. We get infinitely close to 0 on the right side from the branch above the x-axis, but we never touch it. We never actually get there. We also have a vertical break, so we have points above the x-axis and points below the x-axis, but we never actually touch the x-axis, even though it looks like we're getting really, really close to doing that. So the reason we care about this is because this gives us a very specific and unique domain and range. The domain is going to be everything from -infinity to infinity except 0. So we can take the reciprocal of any number we want except 0. We cannot plug in the number 0. So it's -infinity to 0 and then 0 to infinity, just not including that point at 0. The range is actually going to be the same, so -infinity to infinity, but not including 0. So vertically speaking, we can get any output we want, but there's a vertical break in the graph there at the x-axis, there where y equals 0. So what you need to be able to do with each of these parent functions is, one, you need to remember the basic shape. So once we condense a function down to its parent function, we strip away everything excessive. You need to be able to identify the parent function, and based on the parent function, you need to know what shape is the graph of my function going to have. You also need to be able to graph at least 3 points accurately. So if there is a point at the origin on the parent function, you need to make sure that you know where that is, and then you need 1 point, at least 1 point, on either side of that particular central point to be able to graph. So we need to know where some key points are because we're about to start moving things around and changing things. Remember, a parent function is just a starting point. It's the starting point for a graph. So we need to know where we're starting accurately in order to graph everything else that's going to be changed accurately. We call the changes we make to a parent function function transformations. So to get other graphs with the same basic shape as a parent function, we apply function transformations to the individual parent functions. So transformations occur when we multiply or add or subtract onto our original function. Each of these algebraic operations does something different to the graph of the function. It transforms the function in some type of graphical way. So anything that is done directly to x, directly to the input, is a horizontal transformation. So it involves something left to right on the graph. And anything that is done to f of x, in other words, done to the function as a whole, done after we apply the parent function, that's considered to be a vertical transformation, so something up or down on the graph. Now it's important to remember, this is kind of weird, but it's just something you have to remember. Whenever the transformation is horizontal, in other words, whenever we've done something directly to the input itself, we always have to do the opposite of what the function tells us to do. So I always remember this as x always lies. If you just remember that x always lies, that should be sufficient to help you get through this. So whenever something is done directly to the x, whatever the transformation is saying is going to happen, we're actually going to do the opposite of that. So I'll explain that in more detail when we look at the actual transformations. So again, a transformation is just something applied to a parent function that changes it. We're going to generate a graph that's going to have the same shape, but it may be moved around, it may be warped slightly. Our first type of transformation is called a translation or a shift. With this type of transformation, we're literally just sliding the graph around on the coordinate plane, up and down or left to right, or some combination of both. The first possibility is a vertical shift. So to shift the graph up, f of x becomes f of x plus a number. So if we're applying the parent function and then after the parent function is applied, we're adding on a number, that tells us to shift the graph up that many units. Not surprisingly, to shift down, f of x becomes f of x minus a number. So if we apply the parent function and then subtract a number, that shifts our graph down that many units. We also have a possible horizontal shift. And remember, x always lies. So horizontal occurs when we do something directly to the input, directly to x. And whatever x says it's going to do, it always does the opposite. So in order to shift right, we're thinking, okay, we're moving in the positive direction, but remember, x always lies. So if x is saying it's going to go in the negative direction, it's actually going to go in the positive direction. So f of x becomes f of x minus a number. So notice that this is being applied inside of the function. We're subtracting a number inside of the function before the actual parent function is applied. So again, x always lies. So x says it's going negative. That means it's actually going to go in the positive direction. It's actually going to go to the right. If we want to shift left, shift in the negative direction, that means it's going to be f of x plus h. Again, the plus is applied before we actually apply the parent function. So we're adding a number inside of the parent function. So x lies, it shifts it in the opposite direction, which in this case is the negative direction. So anytime we add or subtract a number onto our function or directly onto our function input, that tells us we're going to be moving the graph around on the coordinate plane, maintaining the shape, but just shifting it up or down, left or right. So let's look at some examples of each type of translation we could perform on a graph. So we want to graph f of x is equal to the absolute value of x plus 2. So first thing we need to do to graph any type of transformation is identify the parent function. That's always the first step. So in this case, the parent function is what we have if we strip off any type of addition, subtraction, or multiplication from our problem. So if we pull off that plus 2, what's left is the absolute value of x. So that means our parent function in this case is going to be the absolute value function. The graph for the absolute value function is going to be the starting point for the graph that we want to create. Next we say, okay, we have the parent function, what are we doing to it? Well, the only other thing tacked on to this function is the plus 2. So whatever that plus 2 does to the graph, that is the only change that's going to be made to the parent graph. So since it's an addition of 2 and it's outside of the function, it's applied after we actually apply the operation for the parent function, it's going to be a vertical shift up 2 units. So if we graph this, the dotted line in black is our parent graph. It's the original absolute value function graph. Remember, it's centered at the origin. It's a perfect V, looks like the identity function with the left side flipped upward. Our transformed graph is the graph in green. So we take the exact same shape, take every point that's on the original graph, and we just shift it up 2 units. So the shape hasn't changed at all. The only thing that's changed is where our graph is positioned on the coordinate plane. So our green graph is our actual graph for our function. Let's try another one. So now we want to graph f of x is equal to the absolute value of x minus 2. Notice the parent function hasn't changed. It's still the absolute value of x. And now our transformation is down 2 units. Instead of adding 2, we're subtracting 2. It's occurring after we apply the parent function, after we apply the absolute value. So it's going to be a vertical change. It's subtracted, so we're shifting down 2 units. So we're starting with the same original graph, and then we're shifting that graph down by 2 units. So every point that's on the absolute value graph is shifting down 2 units. Now what about this one? What if we have f of x is equal to the absolute value of x plus 2, where the plus 2 is inside of the parent function? So it's again the same parent function. It's still absolute value. If we pull off any addition, subtraction, or multiplication, we still have absolute value. Now our transformation is applied directly to the input. So we're directly adding on to x. So anything that happens directly to the input is a horizontal transformation. But remember, whenever it's horizontal, whenever it's applied to x, x always lies. So x says go 2 units in the positive direction. Well, if x is lying, that means we need to go 2 units in the negative direction. So our transformation is going to be left 2 units. So we're going to take our parent graph, the absolute value graph, and we're going to shift all the points left 2 units. So in this case, again, it keeps the same shape, but every point is shifted 2 units to the left of where it originally was. Let's try one more. So absolute value of x minus 2. F of x is equal to the absolute value of x minus 2. Again, same parent function, absolute value function. Our transformation comes from the subtraction of 2 applied directly to the x. So applied to the x means it's horizontal. X always lies. X says it's going negative, so that means it's going to shift positive. It's going to shift to the right 2 units. So we start with our parent graph. We shift all the points on our parent graph to the right 2 units. Our next type of transformation is stretching and shrinking. So this type of transformation is actually going to change the shape of the graph slightly. It's still going to be the same basic shape, but it's going to warp it. This is what we call a non-rigid transformation. So it does actually change the shape, not the fundamental shape, but just how far the graph is stretched vertically or horizontally. So for a vertical stretch or shrink, again, vertical is always applied to the function itself. We get a vertical stretch when we multiply the function by a number outside of the parent function where the number we're multiplying is greater than 1. So if we multiply the function by something greater than 1, something bigger than 1, that's going to stretch the graph vertically. So what does a vertical stretch look like? Well, imagine, take the tails on your graph, wherever they are, and pull them away from each other vertically. Whatever that would do to the graph, that's what we consider to be a vertical stretch. So a vertical shrink is when we multiply our function by a number, but the number is less than 1. So anything between 0 and 1, anything that's fractional, if we multiply the parent function by that number after applying the parent function, that's going to be a vertical shrink. So for something like that, same thing, imagine where the tails on the graph are. If we imagine compressing those tails towards the x-axis, so pressing them down vertically towards one another, that's what a vertical shrink is going to do to the graph. For a horizontal shrink or stretch, remember x always lies, it always does the opposite of what it says it's going to do. So for a horizontal stretch, we're multiplying inside the function, so we're multiplying directly by the input, but we're multiplying something less than 1, so something fractional, something between 0 and 1. So x lies, when we're multiplying by something fractional, that's when we're actually going to get bigger. So it's going to be a horizontal stretch. So what would that look like? Well, again, imagine where the tails on your graph are. If we pull them away from each other horizontally, that generates a horizontal stretch. So for a horizontal shrink, again, we're multiplying, but x always lies. X does the opposite of what it says it's going to do. So if we're multiplying x by something greater than 1, the function says we're getting bigger. X lies, we do the opposite. The function actually gets smaller, at least in terms of a stretch shrink situation. So for a horizontal shrink, we're taking the tails and we're compressing them horizontally. So we're pushing them together towards the y-axis. So one thing you may have noticed when we defined what the numbers were that we were multiplying either the function or the input by, notice that none of these situations cover the possibility that the number we multiply could be negative. There's a very specific reason for that. If we're multiplying by something negative, we treat the negative part and the number part separately. Having a negative multiplied actually corresponds to an entirely different transformation that we're going to talk about in a minute. So if you ever have a number multiplied either outside of the function or directly by the function input, treat it as a positive number. If there's a negative in front of it, the negative corresponds to something entirely separate. So treat those as two separate parts. Negatives do something, but they don't apply to a stretching or shrinking situation. So again, if we're multiplying the function or the function input by a number, that corresponds to a stretch or shrink depending on what the number is. So let's try a few of these. First, we want to graph f of x is equal to 2 times the square root of x. So first thing we decide is what is the parent function. Well, if we strip off the multiplication by 2, we're left with the square root of x. So the square root of x is going to be our parent function. That's going to be the graph we're going to start with to generate our graph. Then we need to decide what's happening to the parent function. Well, in this case, we're multiplying on the outside by a 2. Since the 2 is being applied after the operation for the parent function is applied, we know it's going to be vertical. It's going to be a vertical change. We're multiplying by a number that's greater than 1. So if we're multiplying by something greater than 1, that means it's going to be a vertical stretch. So what is that actually going to look like on a graph? Well, remember that means take the tails, or in this case just one tail, and stretch it vertically. So pull it away from the x-axis. Sometimes it'll help with a vertical or horizontal stretch or shrink to have some actual points to graph. With a shift, it's usually easy just to see where everything's going to end up. Stretching is a little different. So what's actually happening here? Well, we're plugging in all the same inputs, and then once we apply the parent function, we're doubling whatever the output of the parent function is. So if you think of how far all of the points are away from the x-axis, in other words, what the y-coordinate is on the original set of points for the parent function, we're now doubling those y-coordinates. So one of the points on the original parent graph would be the point 4, 2. So if we take the square root of 4, we get 2. 4, 2 is a point on the graph. The point on the new graph is going to be 4, 4. So we take the old y-coordinate and now we're doubling it. We're taking double the distance from the x-axis. We're taking a vertical stretch so that we're double the distance away. Another point that's on the original graph is 9, 3. Well, 9, 3 now becomes 9, 6. The point was originally 3 units away from the x-axis. Now we're double the distance away from the x-axis. We're now at 9, 6. So on our graph, what that looks like is a slightly steeper square root graph. So the original square root graph is in the dotted black, and then our actual graph that we're graphing is the green one. It's stretched vertically. So notice if you can identify where those key points are, the ones on our new graph are double the distance away from the x-axis. In other words, we've stretched them vertically by a factor of 2. Well, what happens if we go in the other direction? So now let's graph f of x is equal to 1/2 times the square root of x. Same parent function, starting with a square root function. We're multiplying by 1/2 after the parent function is already applied, so it's going to be a vertical transformation. Because the number we're multiplying by is less than 1, it's between 0 and 1, it's going to be a vertical shrink. So now instead of taking the tail and stretching it away from the x-axis, we're taking the tail and we're pressing it down towards the x-axis. So that means now our points are going to be half the distance away from the x-axis that they originally were. So 4, 2 is now going to be half the vertical distance away. So 4, 2 becomes 4, 1. We cut the y-coordinate in half. 9, 3, if we take half the distance between where that point was and where the x-axis is, half the distance is now going to take it to 9, 1.5. So notice in this case we end up with something that's fractional. That's okay, it's inevitable, it's going to happen. All we want is a rough sense of where these new points are on our graph. So again, the black dotted graph is our original graph. The actual graph that we're graphing, our particular function, is the green one. It's the one that's halfway away from the x-axis. So it's half the distance of where we originally were from the x-axis. Now let's look at our other two cases. Let's graph f of x is equal to the square root of 2x. So same parent function, we're still looking at the square root function. Now we're multiplying a 2 directly onto the input, directly onto x. So because it's being applied directly to the input, it's going to be a horizontal transformation, but x always lies. So whatever x says it's going to do, it does the opposite. So x is saying stretch, so we're actually going to shrink horizontally. When x says double, we're actually going to cut something in half. So what does that look like for our points? Well, in this case, we're changing horizontally, we're not changing vertically. So all of the y coordinates are going to stay the same, the x coordinates are going to change. So x lies, x says it's doubling, which actually means it's being cut in half for our new points on our graph. So 4, 2 is on the original graph, on the parent graph. 4, 2 now becomes 2, 2. So x says double, so we know x actually is being cut in half. So 4 becomes a 2. Now what about 9, 3? So 9, 3 was on the original graph. X says double, we do the opposite. So we take 9 and we cut it in half and we get 4.5. But again, notice that the y coordinates have not changed. We're applying the transformation to the x, not to the y. So our vertical components for our points, those don't change. On our graph, it may be a little difficult to distinguish something like this from a vertical stretch. The only way we know the difference realistically is from the actual function. So we've still got the parent graph on there, black dotted line. The green one is the one we want. So if we were to take the black graph and push it towards the y-axis, push it horizontally, compress it horizontally by a factor of 2, we end up with our green graph. So it is helpful in this situation to have the actual points to have a better sense of what our graph is actually going to look like. So let's look at one more case. So we want to graph f of x is equal to the square root of 1/2 x. Square root parent function, that hasn't changed. Now we're multiplying our x by a 1/2. So it's being applied to the x. It's a horizontal transformation. X always lies. X always does the opposite. So if x says it's being cut in half, it's actually being doubled. So it's actually being stretched in this case. So this is a horizontal stretch. So what happens to our points? Remember, we had the points 4, 2 and 9, 3 on our parent graph. X says it's being cut in half, which means that when we actually apply the transformation, we do the opposite. So if x says it's being cut in half, x is actually being doubled. So 4, 2 is now going to become 8, 2. Notice again, the y coordinates didn't change. All we're changing is horizontally, so we're changing the x's. So 4, 2 becomes 8, 2. And 9, 3 becomes 18, 3. Notice that in this case, this point is going to fall off of our graph. That's okay, we'll just graph as accurately as we can. So we have our parent graph, and then if we were to stretch this horizontally, in other words, take the tail and pull it away from the y-axis, we end up with the green graph, which is a horizontal stretch of our original graph. So now let's look at our final transformation category, reflections. So remember, I mentioned before that when we're multiplying by a number, we consider that number to be positive. Even if it's negative, we treat the negative as being separate from whatever number we're multiplying our function or our input by. The reason we do that is because the negative corresponds to a different type of transformation. In this case, the negative corresponds to our final transformation, which is a reflection. So to get a vertical reflection, f of x now becomes negative f of x. So if we apply the parent function and then we apply a negative, we multiply a negative outside of the parent function, that's going to be a vertical reflection. In other words, it's going to be a flip of the graph across the x-axis. So anything that was above the x-axis is now going to be reflected below. Anything that was below the x-axis is now going to be flipped above the x-axis. A horizontal reflection is going to be a negative applied directly to the input, directly to x. There's really no x lies in this situation. It just is what it is. It's a reflection. It flips across the axis. So in this case, anything to the left of the y-axis is going to flip to the right. Anything to the right of the y-axis is going to flip to the left. So let's look at a couple examples of our last transformation. Let's graph f of x is equal to negative x squared. So what's our parent function going to be? If we strip off any addition, subtraction, or multiplication, in this case we're multiplying by a negative 1, we're left with x squared. So our parent function is going to be the quadratic function, the squaring function, x squared. Now what we need to decide is how is this negative 1 being applied? Is it applied before or is it applied after the exponent? This is where order of operations comes into play. So remember, please excuse my dear Aunt Sally, PEMDAS, however you learned it. Exponent and multiplication are the two things that are happening in this situation. According to order of operations, exponents come before multiplication. So that means we're taking the x and we're squaring it, and then we're multiplying by a negative 1 after that. So in that case, that means we're applying the parent function, the squaring function, before we apply the negative. So the negative is being applied to the function as a whole, not directly to the input x. That means this is going to be a vertical reflection because we're applying the negative after we apply the parent function. So we take our parent function, this case x squared, it's going to be a parabola, it looks like a pretty U shaped onto our coordinate plane, and we flip it vertically. So everything that was above the x-axis is now flipped into a mirror image below the x-axis. All the points are the same except the y-coordinates are now going to be negative for all of our original points. Now what happens if we want to graph this one? What if we want to graph f of x is equal to negative x quantity squared? Same parent function, still the x squared quadratic squaring function. Now we have to decide what's happening here. So according to order of operations, what's happening? So parentheses, exponents, multiplication, division. Here we have a set of parentheses, so notice that the negative is inside of parentheses. That means multiplying by the negative 1 is going to happen before we square the function. So that means the x is directly being made negative, and then we're applying the parent function. If the negative is applying directly to the x instead of being applied after the parent function is applied, that means it's going to be a horizontal reflection. So we're going to flip it left to right. So we take our original function and flip it left to right. Let's look at that one more time. So there's our original function, there's the parent function, and then we reflect it horizontally. Well, what happened? The graph didn't actually change. That's true and it's false. So it was reflected, but notice this graph already had some type of horizontal symmetry. So if we were to flip this graph on itself, even though the points have exchanged places, we don't actually notice it because the points are already mirror images of one another. This is just a special case. If we were to reflect something like, say, the square root function, then we would definitely have an image that looks different from the original. So the only reason this horizontal reflection is not as noticeable is because we already have some symmetry. But all the points from the left move to the right, all the points from the right move to the left. So the last thing we need to do is put it all together. So I'm sure you're aware that you're not just going to be given one transformation. You're going to have a function that has a bunch of different things going on. So what happens when we have more than one transformation applied to our function? What do we need to do? Well, in this case, when our function has more than one transformation, we have a specific order we have to apply them in. They always have to be applied in the same order when there are multiple transformations going on, being applied to our parent function. The first thing we apply is always going to be a horizontal shift. if there is a horizontal shift in our actual function, that's the first transformation we have to apply. If there isn't one, we don't worry about it and we just move on to whatever's next in our list. So after horizontal shifts, we then look for any stretches or shrinks. This can be vertical, this can be horizontal. Typically, you won't have both. You may have one or the other. It's possible you could have both, but it's not likely. So if there's any number multiplied by our function or by our input, we apply it after looking for a horizontal shift. Next, any type of reflections we have. Again, it's unlikely that you'll have both a vertical and a horizontal reflection, but if you do, order doesn't matter in that case. They just both have to be applied after our horizontal shift and after our stretches and shrinks. And then finally, if we have a vertical shift, that's always the final transformation we apply after looking for our other three cases. So let's try an example. So we want to list the transformations for this particular function, specifically in the order that we're going to apply them in, and then we want to graph our function. So our particular function is f of x is equal to the square root of negative x minus 5. So with any graph, make sure you identify the parent function first. So if you strip off any addition, subtraction, or multiplication, what are you left with? In this case, we're left with the square root of x, so that's going to be our parent function. That's going to be the starting point for our graph. Then we need to look at everything else that's in the function besides just the operation in the parent function. So we've got a negative multiplied by the x, and we've got subtraction of 5 applied after the square root. So we go through our list. First thing we look for is a horizontal shift. We get a horizontal shift from adding or subtracting directly onto the x. In this case, nothing is added or subtracted directly from the x, so we don't have a horizontal shift. So we don't have one of those, we go to the next. Now we look for anything that would give us a stretch or a shrink. Stretching and shrinking comes from multiplying by something other than 1 or negative 1. So multiplying by something greater than 1 or multiplying by a fraction, either onto the function or onto the function input. Neither of those cases are happening here, so we don't have a stretch or shrink. We go to the next step. The next one is reflections. We have a reflection if we're multiplying by a negative. So either the function itself is multiplied by a negative or the input is multiplied by a negative. In this case, x is being multiplied by a negative 1. So that means we have a horizontal reflection. That is going to be the first transformation we apply to our particular parent graph. Last but not least, we look for a vertical shift, so adding or subtracting after the parent function has been applied. In this case, we're subtracting 5 after taking the square root, so we have a vertical shift down 5 units. So what is this going to look like when we graph? Well, we're going to start with our parent function, square root of x, and we're going to individually apply each of these transformations in the order listed. So our first transformation was a horizontal reflection. So we're starting with our parent graph, the square root graph, which is the one in black, dotted line in black, and we're reflecting that graph horizontally. We're reflecting it across the y-axis. So after one transformation has been applied, we've now moved from our parent graph to the green graph, to the reflected square root graph. Our next transformation is to move down 5 units. So what we're going to do now is, as opposed to starting with the parent graph, we're going to start with the reflected graph. So we applied one transformation. That's now going to be the starting point for our next transformation. So we're starting with the green dotted line, and we're shifting it down 5 units, and we end up with the orange graph. So the orange graph is going to be our final graph. That graph has been reflected from the parent function and then shifted down 5 units. So that graph is our final answer. So one thing to keep in mind when you're doing a problem like this where there's a bunch of transformations, the only thing that's absolutely required is that final graph. All the other guidelines are really there just for you, just for your purposes as you're graphing. That's the only part that's actually required for an answer. Now, while you're practicing graphing and while you're getting used to this, it is helpful to write all the intermediate graphs in. So graphing the parent graph, and then in this case, the reflected graph. It is helpful to have those there so you're not trying to jump and do a bunch of transformations at once. But once you've had enough practice with this, if you can immediately see where the final graph is going to be, that's the only thing you need to actually have in your final answer is the final graph fully transformed, all transformations applied. Let's try one more. So now we want to graph f of x is equal to negative 1/2 times x minus 2 quantity squared plus 3. So we're going to list the transformations in the order we're going to apply them, and then we're going to apply them to the graph and actually generate the graph. So what is our parent function for this one? Well, if we strip off all the addition, subtraction, and multiplication, we're still left with something being squared. So our parent function is going to be the x squared, the quadratic. Now we need to go through our list of transformations. So first thing we look for is a horizontal shift. Horizontal shifts are additions and subtractions applied directly to the x. So in this case, we have x minus 2. We're subtracting 2 from x. X always lies, so x says it's going negative, which means it's actually going positive. So our first transformation is shifting right 2 units. Okay, so next we look for stretches or shrinks. Those are always going to be multiplications. In this case, we're multiplying by a 1/2 out front. Remember, we treat the negative and the 1/2 as being separate parts. So just the 1/2 is what we care about right now. The 1/2 is being multiplied after the parent function is applied. So if it's after the parent function is applied, after we're squaring in this case, it's going to be a vertical transformation. Because it's half, it's something between 0 and 1, we're multiplying the function by a fraction, it's going to be a vertical shrink by half. So if we take the distance from our graph's x-axis on the original graph, we're going to cut that distance in half. In other words, all the points are going to be compressed vertically. Then we look for any reflections, so multiplying by a negative. Again, we pointed out that in this case, it's multiplication by a negative 1/2. So the 1/2 part is a shrink. The negative part out front is going to be a vertical reflection. So after we shift right and shrink vertically, we're now going to reflect across the x-axis. We're going to have a vertical reflection. We're going to flip it upside down. And last but not least, we're looking for vertical shifts. So adding or subtracting onto the parent function after the parent function has already been applied. So we're adding 3 onto the end of our graph. So adding 3 is going to shift our graph up 3 units. So in this case, we have 4 transformations, one of each type. We apply each of them to the parent function in this particular order. And then once we've applied our vertical shift, the graph we're left with is going to be our final graph. It's going to be the graph of the full function. So our first transformation is to shift our parent function right 2 units. So our parent function is the quadratic, it's the black dotted line. We're shifting that graph to the right 2 units. So all the points on the original parent graph are now shifted right 2 units. Our next transformation is a vertical shrink. So we're taking the second graph, the graph we found from the shift, not the parent graph, but our current graph, the green graph, and we're going to shrink it vertically. So we're going to take the tails of that graph and we're going to press them towards the x-axis. So it's essentially going to become a wider graph. And I'm not going to be super picky about how accurate your points are at this point. As long as it's clear that you've shrunk your graph, that it's been pressed down vertically, so it's a wider parabola, a wider U, then that's sufficient. So we started with our parent graph, we shifted it to the right, and then from that shifted graph, we've now shrunk the points down so that they're closer to the x-axis. Our next transformation is a vertical reflection. So we've shifted, we've shrunk, and now from that shifted, shrunk graph, we're going to flip it across the x-axis. So now it's the blue graph. Our blue graph is our current one. So that one is shifted 2 units, cut in half, in other words, a vertical shrink, and then that shrunk graph is now reflected across the x-axis. We have one final transformation, up 3 units. So we're taking the graph that's been shifted, shrunk, and reflected, and we're shifting that up by 3 units. So our final graph is going to be this graph here in purple. That's the only one that's really required for a final answer, but of course getting to that final answer without the intermediate graphs may be difficult. So our final graph, again, just to sum up, has been shifted 2 units to the right. After it was shifted, it was then shrunk vertically, so the tails on the graph were pressed toward the x-axis. After it was shrunk vertically, it was then flipped across the x-axis, a vertical reflection. So all the points are now mirror images below the x-axis. And then our final transformation was to take that reflected graph and shift it up by 3 units. So let's summarize what we've learned in this video. Again, we talked about graphing functions. Parent functions represent function categories. There are starting points for any particular function we want to graph. All of their functions generated from the parent functions are going to have the same basic shape. So again, these are the graphs we start with. Based on the fundamental operation that's being applied to our input, that tells us what the basic shape is going to be for our graph. So we start with this basic shape, and then we go from there. So the changes we apply to parent functions are called transformations. They change either the shape or the position of the graph a little bit. So we have 3 types of transformations. In each case, we have a vertical and a horizontal version. So our first type of transformation is a shift. So shifting occurs when we add or subtract either onto the function, that's going to be a vertical shift, or add or subtract onto the function's input, that's going to be a horizontal shift. A stretch or a shrink comes when we multiply the function or the input by a number. Remember, the number we multiply by is going to determine whether it's stretching, in other words, pulling the tails apart, or compressing, pushing the tails together. And then finally, we have reflections. So if we multiply the function or the input by a negative specifically, that's either going to reflect our graph vertically if we're multiplying the function by a negative, or horizontally if we're multiplying the input by a negative.